This is Software Engineering Radio, the podcast for professional developers on the web at se-radio.net. SE Radio is brought to you by the IEEE Computer Society and by IEEE Software Magazine. Online at computer.org/software. Are you a tech-savvy developer with an inquisitive mind? SE Radio has an opening for a new volunteer host to join the team and produce 5 episodes per year. Contact show editor Robert Blumen at robert.blumen@gmail.com for details.
Welcome to Software Engineering Radio. I'm your host, Jeff Doolittle. In this episode, I'll be discussing Antifragile Architecture with Barry OReilly. Barry is CEO and founder of Black Tulip Technology. He specializes in designing anti-fragile software systems. He is a certified information technology architect professional who has held chief architect positions at Microsoft and at iDesign. He has been a startup CTO, the worldwide lead for the solutions architecture community at Microsoft, and founder of the Swedish Azure User Group. Barry is also a trainer for IASA, the International Association of Software Architects, and a research student in the area of complexity science and software engineering. Welcome to Software Engineering Radio, Barry.
Thanks, Jeff.
So in a conversation before this episode, you said something interesting. You said, all really good architects know something is wrong, but can't articulate it. Let's start our conversation there. What is wrong that architects notice but struggle to articulate?
Well, I think if you look at the experience of even really good architects who've had considerable success across sometimes very lengthy careers, there's a discomfort that exists because we all know that being able to reproduce what we do or being able to articulate or describe what we do as architects, being able to mentor and teach junior architects how to react in different situations is incredibly difficult. And if you discuss how a particular architect went about solving a particular set of problems, what you'll find is that there's a lot of intuition involved, and intuition is something that's very difficult to explain and even more difficult to teach. And we know that in a lot of our projects that there's always an element of luck and that things are very, very rarely in our control. Even though if you go to a conference and watch an architect talk about what they've delivered in a particular project, you'll see them talk about how we did this and then we did that and then we seen this problem come in and then we solved it. But we all know that that's not how it works in reality. There's a lot more iteration, there's a lot more mistakes, and the people who are able to consistently deliver don't have a consistent framework for delivering. So there's no single method or approach that actually helps you guide you to be able to deliver architecture, especially when the domains that you're working in are complex. And this makes us very uneasy as architects, and it's a very difficult conversation to have because very few people are brave enough to stand up and say, I'm not exactly sure what I'm doing all the time. And it's not really part of the culture of our industry to be able to say that.
Interesting. So a question there, you mentioned even that there's an element of luck, or that a lot of people, when they present about architecture, very often they're giving us the success and they're giving us the things that they identified that they did. But it sounds like you're saying there's other elements or other factors that might have led to their success that either they're not mentioning or perhaps even they're not exactly aware of. Can you expand on that a little bit?
Yes, absolutely. So in any successful endeavor in a complex environment, there are going to be elements of luck because by definition, a complex environment is something that we don't understand, can't model, and definitely can't control. So there are always some elements of luck in that, but there's also the fact that there is no framework, there is no method, there is no step-by-step process that we can execute on in order to be able to cope with and deliver in that kind of environment. You need to develop a certain set of skills that you aren't going to be able to predict before you start a project, how that's going to work, what you're going to do, how you're going to execute. And so that's what makes us as architects a little bit uneasy, because we live in a world that's that defines competence through our ability to plan and to execute. So there's a British researcher called Ralph Stacey, who's a researcher within complexity and management. And he wrote a fantastic book called Complexity and Organizational Reality. And Stacey talks about something called the dominant discourse of management. And the dominant discourse of management tells us that the world works in this particular way, that very smart people, usually management, get together, they look at a problem, they analyze the problem, they decide on a solution, they execute, they deliver the solution. And if the solution works, then they're deemed to be competent. If the solution doesn't work, then they're deemed to be incompetent. And in complex situations, that never actually happens. And so what we do, and if you go and a tip for reading on this area is the absolutely fantastic and groundbreaking book by Nassim Taleb. It's called Fooled by Randomness. What we do is when we succeed or when we fail, we then make up a story afterwards about what it was that we did, how we decided to execute. And those stories are always much more linear than they were in reality, because no one ever wants to admit that we didn't know what was going to happen. We weren't in control the entire time. And successful architects learn how to be successful when they're not in control all the time. They don't have to predict every step in a project or every product choice or every component choice. They have to predict everything perfectly. And in fact, it very, very rarely happens like that. And if it does happen like that, then you're working with something that's very, very simple.
Okay. So you mentioned simplicity just now, and previously you mentioned complexity. So perhaps you can help expand a little bit on what is it that makes architecture, in particular software architecture, a complex environment versus a simple environment?
So software projects can be simple. They can also be complex. If you want to understand the difference between these things, there's a fantastic framework called Kinevin, which was developed by a guy called Dave Snowden, that helps us to navigate the kind of problems that we're trying to solve and helps us orient ourselves and understand, am I working with a simple problem, a complicated problem, or a complex problem? And simple problems are things that we all understand. If I say to you, make coffee, you understand what to do. I don't have to communicate a whole bunch of detail, and there's hopefully not a whole bunch of things that can go wrong while you're doing that. Complicated things are things like cars and airplanes that have a lot of moving parts and have to be put together and often need expert analysis in order to make them work. Complex things are things that are beyond our understanding, things that we cannot predict, things that we cannot control, things where we do not have a scientific understanding of the behavior of the system. Things like the weather, human systems, economic systems, human behavior. Things can't be modeled with equations or predicted accurately.
So would somebody possibly argue that software is complicated rather than complex based on the definitions that you just gave, or what might differentiate those things?
Yeah. So the thing that differentiates software is that it is, most of the time, software is complicated. And when we say complicated, it means that something requires expert analysis in order to be able to get it to work. The vast majority of the software that we build is complicated. The difference with software and other mechanical things that are also complicated is that we take this complicated piece of software and we force it to live in complex environments. So I take my complicated message bus and APIs and clients, and I put them into a complex environment. And that complex environment is a social system of people, of users, of businesses, of markets. And those things are constantly warping and changing, as well as the technology around them, which is constantly warping and changing. And we force these complicated systems to live in complex environments.
Interesting.
And we make two mistakes as architects and engineers. The first mistake is that we assume that complexity exists in our software. And you'll see this if you ask any hardened programmer about complexity, they'll talk about big O notation and cyclomatic complexity because we're too inward looking. We believe that complexity exists in code. That's not true most of the time. The other thing that we do is that we shut out complex and we focus on the complicated. So we don't care about the people, we don't care about the markets, we don't care about the complex environment that we make our software live in. We only really care as far as the compiler, and then it's someone else's problem. In a complex environment, a complex environment is determined by the fact that all of the agents, all of the acting parties in a complex environment are intensely interconnected. And so the connection between your software components, your decomposition, your choices, and the market and the people around that software are so deep that you cannot do a good job as an engineer if you ignore them or if you leave those things over to someone else.
So you're saying that it's the environment that we put these software systems into that is complex. So while the system itself may simply be complicated, the environment in which we're either deploying it or building it or managing and maintaining it is what brings in the complexity.
Most of the time, yes. So one of the ways that we as humans work with complex systems is that we constrain them, and we constrain a complex system until it's simple enough for us to cope with and manage. And a good example of this is driving. So the driving of cars. When cars first appeared, there weren't any rules, there weren't any regulations, and if you had just bought your car around the beginning of the last century, and you were driving down the road and someone was driving towards you, there was no protocol about what you should do. And so eventually we started to constrain the system. So we said, right, well, we're going to drive on this side of the road or this side of the road. And then we add more constraints. We put white lines on the road. And then we add even more constraints. We come with roundabouts and eventually traffic lights and things like driving licenses until it all seems fairly obvious how we drive. But if you took someone from 1910 in one of the first motor cars and made them drive for example, in Italy today, they would find it kind of chaotic. They would not believe that it's a simple system. So what we do is we constrain. And if you look at what's happening in our industry, what we're doing in cloud is, a computer or processor is actually a complex thing because anything can happen. And what we do is we use hardware architecture and we use software architecture to constrain the possible things that can happen. And this is our both at the hardware level and the software level. This is our white lines and roundabouts and our compiler rules and things like that, and our networking rules. And eventually, when something becomes simple, it becomes a commodity. And the growth of cloud is that commodity. We constrained the computer so much that we can stuff millions of them in a container in a warehouse somewhere and have people plug into it. So we've conquered the complexity of computing through constraint. That doesn't mean that those systems aren't complex, because complexity never really goes away. If one of those constraints or something changes, complexity is very quick to rear its head. But we've pretty much got this one down to a level where we don't need to think that much about it. And as software engineers at enterprises, it's not our job, because people at Microsoft and Google that deal with that kind of constraint, with that kind of complexity. The complexity that you and I have to deal with every day is that when we build a system based on these cloud platforms, we deliver it into these complex environments where there's a completely different and much more difficult a set of concerns that must be addressed. And the thing that I always do in order to get people to understand this is ask a very simple question of an architect or a developer. What will your system do? How will your system behave if a competitor drops their price? In the world of business, in the world of trade, there are an infinite number of things that can happen. It's an incredibly complex environment. And a competitor dropping their price is actually something that we expect. It shouldn't really be a surprise. And if you ask a business person, a CEO or a CFO, what are we going to do if a competitor drops their price, then they'll generally have a good answer or to that question. If you ask a developer, you generally get a blank look. As in, that's not my problem.
Right.
Now, if a competitor drops their price, the business has to respond in some way. You have to drop the price yourself, which impacts your margins, or you have to get out of that market, or you have to change your offering so that it moves perhaps from a product to a more service-oriented offering, or perhaps you want to buy that competitor, exit that market, move to a different adjacency. There's a whole bunch of choices that can be made, and every single one of those choices is going to have a massive impact on the architecture of the system that you've put in place. The vast majority of systems that we build, because we're inward looking, because we think that complexity is inside the software, we focus so much on the software, we don't understand the impact that that kind of thing can have on the perceived and the actual quality of our software.
So that's an interesting point. It sounds like you're making a connection there between the need for software engineers and architects to have a better understanding of the business environment that their software lives in. Is that right?
Yes, and that's an argument that architects and architecture organizations like IASA, the International Association of Software Architects, have been making for 15 years. But it's always been abstract, and it's always involved telling senior developers that you need to know about business, you need to know about the business, you need to know about how the business works, and otherwise your career will stall. My approach to that is to say you need to understand how your business works. You need to understand how business works in general. Otherwise, your systems will fail eventually.
Okay.
In these complex domains. And I believe that we're moving, as an industry, we're moving towards a new era. And so back in the 1930s, business was something, in my mind, was done by large men with cigars around fireplaces.
Sure.
And in the basement, they had the finance geeks, and the finance geeks were doing sums and ledgers and things like that. And at some stage around the time of Bretton Woods, the finance people were invited up to the fireside. They never really left. And we've seen that at its pinnacle in the 1980s. And I believe that we are on the cusp of being invited to the fireside, because we've been in the bunker for a very long time, and deservedly so, you might say. And we are about to be invited to the fireside, where we don't become an organization that delivers software into a business, but we become a vital functioning part of a business, building and delivering and refining software. And so our ability to respond in step with a business, as part of a business, rather than something that delivers to the business, is going to fundamentally change our relationship with stakeholders, which means that when a competitor drops their price, it's our job to be on that and make sure that we react in time.
So we've talked a lot about complexity so far, and you mentioned before Nassim Taleb and the book Fooled by Randomness, but this might be a good place to segue into another one of his books, since our episode is titled Antifragile Architecture. So maybe you can make the connection for our listeners between complexity and the concept known as anti-fragility.
Complexity is something that, as I said, the vast majority of people don't really understand, and they have very little reason to understand it. And the key thing to understand is that there is a very big difference between something that's complicated and something that's complex. Something that's complex is inherently non-linear in nature. It's unpredictable, uncontrollable, and it's beyond the reaches of our science. Now, we're programmed as people to seek patterns, to understand things, to map things out. And especially in the business world, as I mentioned, Stacey's dominant discourse, it tends to make us seek certainty. And that seeking of certainty gets us into an awful lot of trouble, especially as software engineers. Complexity is a very difficult subject, and I think that Nassim Taleb has done a fantastic job of writing books that give you an introduction to complexity without all of the heaviness that you might find in other complexity literature. Fooled by Randomness is a fantastic start. It tells us about our place in the universe and the fact that we don't really understand what's going on most of the time, and that we tend to invent little stories about how things have happened, and use things like hindsight bias to convince ourselves that somehow we're in control. Antifragile is a continuation of that, and in Antifragile, Taleb investigates the kind of systems that, when they're exposed to randomness, when they're exposed to the stress that's inherent in being exposed to randomness, that these systems, rather than crumbling, as some systems would do, rather than simply weathering the storm, these systems actually use the stress of randomness that they're exposed to in order to become stronger. And the standard example of this is when the plague came to Europe in the 13th, 14th century. When plague came to Europe, a lot of people got sick and a lot of people died. But now, 600 years later, we're still here. We're significantly better off than we were before. There's a lot more of us than there were before, and very few of us are going to die from pneumonic or bubonic plague. So our immune systems and as a collective system, European society was able to react to a form of stress that it had never seen before, which we call a black swan, something that we couldn't have predicted. We've become stronger and better for the exposure to that stress, even if we suffered for a short while during that. And the concept of anti-fragile then is any system that's able to not only absorb but to use stress to make itself stronger. And if you look at any system that we consider to be anti-fragile, which is resilient or beyond resilience, as Tulip would say, you'll see that most of those systems, the human immune system, economic systems, political systems, they have become strong. They've become resilient. They have grown beyond resilience through the exposure to stress. Not through design, not through some kind of central committee, not through some magical method that makes everything work, or some governing framework, but through the exposure to stress.
So stressors and complexity, it sounds like there's a relationship there. We spent a lot of time earlier on talking about complexity, and now in the context of anti-fragility, you've mentioned stressors. So maybe you can explore that connection a little bit.
So one of the things that happens if you're a software engineer and you read the book Antifragile, you cannot help yourself from drawing parallels with our industry. And the inevitable question that you're going to ask yourself is, why don't we build systems that get stronger as they're exposed to stress?
Exactly. Yes.
And the truth is that we're not really, we don't really have the right way of thinking to do that, because we gather requirements, we build to those requirements, we test to those requirements, and we deliver things into production, which is the exact opposite of building to anti-fragility. And there's a guy called Kenny Jones at NASA who wrote an article on how we need to rethink how we do design, because building to requirements automatically makes a system fragile. If you build a system that's only built to satisfy its requirements, which are very often wrong, confused, and muddled, if you build a system that will only satisfy its requirements, then that system is naturally going to be fragile to everything that you haven't built it to be able to do. For example, if you build a system that has a spec that says we need to have 500 calls per second coming into this system, if that system falls down at 501 calls, then you technically and contractually have done your job. But the perception of quality in the minds of the people that you've delivered that software to is that you've delivered something with a fairly low level of quality. And so in the minds of many of our customers and our partners that we work with, quality is a measure of how well a system responds to complexity, not how well a system responds to a spec that was written several years ago and nobody can remember who wrote it or why. And so what we need to do is to start rethinking, how do we design our systems? And the concept of stress is very, very important. Now, there's a guy called David Parnas back in 1972 who wrote an article on decomposing a system into modules. And he talked about how we as software engineers tend to break a system down into functional components, something that he called conventional decomposition. And that this was quite damaging and limited the life cycle of a system. In the next step, then, he said that we should do something called non-conventional decomposition, where we break a system down and according to what is going to change. And that's a fantastic idea and definitely an evolution from what we've been doing previously. And it turns out that we pretty much ignored what Parnas said and continued breaking the systems down according to function for many, many years. And we're still doing it today. But beyond Parnas, then, if we look at complex systems, if we look at the system outside the piece of code that we're going to build, it's actually impossible for us to determine what's going to change in a complex system. Now, we might be able to, there are some obvious things that are going to change. So you shouldn't hard code your database strings. You shouldn't weld your system to a particular operating system. These things are fairly obvious, and standard systems engineering should take care of that. And so there are things that will change, and you design a system for those things that are going to change. It's going to be a little bit more robust than a system that's not designed for those things that are going to change. But outside of that, in a complex environment, there are millions and millions and trillions and an uncountable number of things that can possibly change. And when those changes happen, they will produce stress on your system. And rather than identifying all these individual things that are going to change around a system, which is impossible in a complex environment, we need to be able to talk to the ability of the system to withstand stress. And that removes us one step from talking about things that may change in an environment, because we're never going to be able to do that. We're never going to be able to predict it. We're never going to be able to agree on what to focus our energy on. So instead, we focus on what kind of things are going to stress a system. And if we do that, it gives us a much better opportunity to actually investigate something which we tend to ignore in our industry, which is how does a system behave when we put it into production. So our industry tends to focus on the functionality, on the use cases. And what we need to become much more aware of if we're going to build systems and deliver them consistently and well into complex environments is how does the system behave? How does the system cope with spikes in load? How does the system cope with changes in the market around it? How does it cope with social changes and changes in social attitudes around it? And any system that we build to be more resilient towards these kinds of things is going to have a higher level of quality than those that we've delivered before.
So are you saying that use cases and functional requirements are not necessary, or are you saying they're not sufficient?
I'm saying that they're not sufficient. They're absolutely not sufficient. So requirements are a very, very difficult thing in the complex environment which I've described. Outside of the software, we have some kind of business function that we're delivering. One way that we deal with complexity as human beings is to outsource it, is to make it someone else's problem. And so when I, as an engineer or an architect, go to someone in my business and say, tell me your requirements, what I'm actually saying is I'm outsourcing the problem of complexity to you so that when this project fails, it's your fault. And it's actually a form of bullying that we do to our partners, to our business stakeholders. Use cases are also something that are an issue for us. As I mentioned before, we as human beings are pattern seekers, and we'll look for patterns, and we'll base that on our previous knowledge of the world, something called precedence, and we'll look for patterns, and very often we'll see things that aren't there, which is good because it promotes action in certain cases. But use cases are a package of things, or a package of requirements and flows of information that are actually quite dangerous, because there's a whole bunch of assumptions baked into those use cases. And so I tend to not use requirements, definitely not at the start of the project, and I never really use the concept of a use case. What I tend to do is to break a system down to the interactions between the actors in that system. And as we're building information systems, then the thing that's interesting to us is the flow of information between actors in a system. And so the basic unit of decomposition for me in a system is a flow, when a piece of information moves from one actor in a system to another. And that means that we take away all of our bias and all of our preconceived notions about how a system should work. And it means that we investigate that fundamental unit in an information system that actually that we know is going to happen. And when we do that, that gives us a base to understand the system in a much, much better way. If we're going to build something that's more resilient, or something that tends towards anti-fragility, then we need to make sure that these flows of information can keep happening, or can happen in a slightly different way. And so it's the flows of information that's important to us as a modeling concept, not the requirement and not the use case.
Okay, so let's dive a little bit more into that. You mentioned something called flows and information flows, specifically in the context of stressors. And as we dive into that, I imagine there's some question in people's minds about not considering use cases and not considering requirements. But at some point, users are going to expect their features. They're going to expect that the system does certain things. So how do we get there using this approach of flows? And maybe you can talk a bit more specifically about how that works, how you identify the flows, how you identify the stressors that they address, and how to answer that question that people might have, because it sounds a bit disconnected, I think, for some people to understand, how am I ever going to give my end users what they want if I'm focusing on what may feel like a very abstract approach to the problem?
Yeah, I understand that. And so eventually we will deliver those features. That's the purpose of what we do. But what we're doing now, before we start to build a system, is that we are taking a step back from functionality and we're focusing on the system's behavior. So at the very base of every project we ever do, there's a business case and there's a business model that we're trying to accomplish, we're trying to execute on. And so everyone has a rough idea of what the system should actually do, what it should achieve. And we tend to break that down to features way too quickly. And the reason for that is that we want to get started developing. And when we do that, then we lose control of the behavior of the system. And a great deal of my consulting work involves actually rescuing projects that have crashed. And in almost all of those projects, I see this rush to deliver features, but there's nothing wrong with that in itself, but the fact that the system's behavior is ignored. And so what we do in anti-fragile systems design is that we start by focusing on stress. We say, here we have a business model. That business model is going to require some form of support in terms of software. What kind of things can stress this business model? And so we start with the obvious one. What happens when a competitor drops their price? And so what I allow developers to do, because the truth is that system decomposition is mostly random, mostly based on intuition, and very often based on the last blog article that your lead developer read. And so what I do is allow people to decompose the system whatever way they want. Okay, so Parnas wrote about functional decomposition in 1972, and we're still doing it in 2019. So it seems quite instinctive. So you won't really get anywhere if you're constantly beating people up and telling them that they have to change the way they do things. So we allow them to decompose the system whatever way they want, and then we say, now we're going to start applying stress to this system you've designed. And so the first stress is always, what happens when a competitor drops their price, in order to get the engineers to start thinking that this complicated thing that you're building is going to live in a complex environment where you won't be able to predict everything that's going to happen. And so we change the design a little bit and we say, well, if a competitor drops their price, the business is going to do this. And so we're immediately promoting a different conversation with our business stakeholders. We're asking them, we're not saying, tell me your requirements. We're saying, tell me what will happen if a competitor drops their price. And then we adjust the system not necessarily so that the system copes with that price drop automatically. Although we'll take that if it's there and it's easy, but that we build the system in such a way that there is a path to coping with what's going to change. And the second stressor, which always makes people very nervous, is lizards. And so I tend to tell people that the next stressor you're going to deal with is giant fire-breathing lizards are going to come up out of the sea. They're going to destroy the city. How does the business cope with this? And that seems ridiculous, and it's ridiculous for a reason, because I want people to stop thinking about probability. Because when you start thinking about stress, people tend to go into risk management mode, and risk management is not what we're doing here. We're doing design, and risk management always thinks about probability, and probability is a very dangerous subject for us because it's filled with bias, and none of us actually knows the future. We're completely hopeless at probability as a species. So what we need to do then is solve this problem. What are we going to do? How are we going to solve for fire-breathing lizards? And we move our design around a little bit, and we put a redundant data center in a different city that might not get hit by these fire-breathing lizards, and maybe we want to make some things fireproof. And so we're getting into the actual behavior of the system. And even though it might seem like a complete waste of time if you're a project manager, what we've actually done is we've shifted the design around, and we can now cope with a whole bunch of different stressors. We can cope with fire, we can cope with flooding, we can cope with war, we can cope with power cuts, and we can cope with social unrest. We've solved a whole bunch of problems, and we haven't even had to think about them. And that's the definition of anti-fragile, is to be able to respond to stress that we'd never seen before. So by exposing our design to the imaginary stress of lizards, we've made it stronger towards a whole bunch of things that we haven't had to think about yet. And so what we do in what I call a stressor analysis is that we just take a spreadsheet and we make a list of all these things that stress the system. And it's easier to talk about stress than things that will change. Because remember, we can't predict what will change, and the list is too long. We can never get to the bottom of it. And so I create, and it's quite easy to, once you get people engaged in this, it can be quite fun, and you come up with a massive amount of stress. And these lists can be quite long. And every time, and what you do is you take one set of your stressors and you use those to design the system. And you say, what changes do we need to make in our design in order to be able to cope with this kind of stress? And the design, then, we're actually pushing the design into the same kind of process that real world anti-fragile systems have been a party to. And the reason they become anti-fragile is that they're constantly stressed. Except we're doing this over the course of a few days and it's costing us almost nothing. We reserve a set of stressors then, and we borrow a trick from machine learning. We use the first set of stressors as our training set and the second set of stressors as our testing set to see, does the model actually work? And if we've increased the level of resilience in our system, then what we should see is that we will solve this solution will meet the problems, it will survive the problems, it will become stronger when exposed to the problems that it hasn't been told about. And that's the definition of anti-fragility. A system that can survive things that it couldn't possibly have predicted, it couldn't ever have seen. And that gives us a very, very simple tool that does two things. One, it makes our systems massively more robust and more resilient, regardless of whether or not we believe in the ability of a system to become anti-fragile. It makes us much, much more aware about the stress that exists in the system, and it makes us closer to the business. All of those three things are on the architect's dream ticket, and one simple tool does this for us.
Okay.
Yeah.
So you focused a bit again on stressors there. I feel like I'm still a little fuzzy on flows specifically. So maybe you can speak more to those.
Yeah, so we're getting to flow. So when you expose when you have a system that's anti-fragile, there's a Norwegian researcher called Kjell-Jørgen Holle who wrote a book on anti-fragile ICT systems where he investigated the concept and said, is it possible for an IT system to be anti-fragile? He came up with 4 features of an anti-fragile system. And he said, yes, it is possible. There are anti-fragile IT systems. Microsoft's Azure, Amazon's AWS, great examples of this. And he came up with these 4 properties: modularity, in that systems are made up of modules; weak links, in that the modules are weakly linked to each other; redundancy; and diversity. And what you'll find is every time you're tweaking your system, every time you expose it to stress and you change something, it will inevitably be one of those 4 things that you're changing: the level of modularity of the system, the linkage between the modules, the redundancy and diversity of the components in the system. And so what we want to do then is to be able to, once we've come up with our stressors, once we have a rough shape of our architecture, then we want to say, how do we break this system down into a number of components? And we do that by investigating our system as a number of flows. And as I said, the flow is the basic unit of work in any information system. And so we write down a list of flows, and then we do some analysis on those, and we take a tool called the design structure matrix, which is something they use at MIT to decide which components belong together inside a single component and which components need to live their own lives outside of this. And this design structure matrix is just a matrix of flows against each other, and we look for dependency between flows. And out of that, we see which flows need to live together. And we introduce some heuristics, some rules about these flows. We say that information can go into a flow and it can leave a flow and then go into another flow. But information can never from inside a flow cross the flow boundary and go to another flow. It has to exit the flow. And so in that way, we're creating these flows as modules in our system. And then inside a flow, we say, well, what has to happen inside this flow? The example I always use is a bicycle shop. So we have a flow called order bicycle, where information flows from me, the consumer, to the company saying, I would like a red bicycle with a bell and 2 wheels. And that flow, then we look at that and we say, well, what needs to happen in order for this flow to execute? And it says, well, we need to check that this is a registered customer. We need to check that we actually have this type of bicycle in stock. When we need to make sure that we have information, payment information, and how we're going to ship this bicycle to this customer. All of these things have to happen for the flow to execute. And so what we want to do then is to make sure that all of this code that has to be written is grouped into components, and those components will consist of a number of functions. And what we then do is that we go back to our list of stressors, and we produce a stressor flow and a stressor component matrix, and we say how many of the flows are impacted by this particular stressor, and inside the flows how many components are impacted by a particular stressor, and inside the component how many functions are impacted by a particular stressor. And now we're back in the world of Parnas, and I call this Parnas counting, where we want to see how many components, how many functions are actually impacted by a stressor. And we look for these patterns of stress in our components through our flows, components, and the functions that make up those components. And anything that has a similar pattern of reaction to stress gets to live in the same box. And this is how we build up that modularity and that weak linkage that's necessary for an anti-fragile system. And this is the balance that we have to find, because we cannot put every function in its own isolated module weakly linked to the rest of the system, because that way lies madness. And so this allows us to
millions of microservices all interconnected, right?
Yes, and a lot of people are trying that, and good luck to them. But so what we're actually doing with this concept of stressor and flow and playing the two things off each other is that we're making guided, rational decisions based on the stress that a system's going to be exposed to, from the complex environment that we're forcing it to live in, about which components, which functions should be grouped, which components should be grouped, and which flows should be grouped. With the concept that if a stressor acts on the system, what we want to do is to prevent contagion. So if a stressor acts on your system, you want to make sure that the impact of that stressor hits as small a surface area of your system as possible. And that is how we get towards a system having these 4 properties of anti-fragile systems. And we've also tested it with stress, so it's not a theory. We've actually seen that our design responds to the kind of stress that may exist in the system. And we haven't tried to predict the future, and our stressor list is incomplete, and it's always going to be incomplete. And the mission that we're on here is to be able to build a system that responds to stress that it won't have seen, won't be aware of before we put it into production. And that's the gist of anti-fragile systems design.
So basically, because you've accommodated many kinds and categories of stress, which you're not trying to taxonomize or put into patterns again, but you've covered enough, as you mentioned before. If you can handle the fire-breathing lizard, you can by definition handle other stressors that you have conceived of and others that you have not even conceived of. The goal is not certainty. The goal is covering your bases with enough stressors that you have a high likelihood of survivability or even improvement when there's chaos in the system. Am I getting that right?
Yes, exactly. And so the difference between what I'm talking about now and risk management, this is a real tough point for project managers to understand. I don't actually care about the particular individual stressor incidences, because if you just take individual stress and encapsulate it, you're not actually doing anything. You're saying that this system will work if I have correctly predicted the future. And we know from what we said about complexity earlier that no matter what happens, you have not correctly predicted the future. It's not possible in a complex system to do that. And so encapsulation is not the goal here. What we're trying to do is to promote the kind of properties in a system that we see in systems that are highly resilient and even beyond resilient and anti-fragile. So we don't care about the individual stress. We care about the behavior of the system connected to stress in its environment. And what this gives us then is a modularization of our code based on flow. And so we have these 4 really important concepts: stressor, flows, components, and functions. And our system is dependent on these things. Now we can start, once you start asking questions about stress, what you'll find is that you start to get requirements, really high quality requirements. Because I'm not saying tell me your requirements, which puts a business person on the spot and forces them to answer even if they don't, they can't really answer. You start to get a clear picture of non-functional requirements, which is a very difficult thing and something most architects struggle with doing, and something most business people just aren't capable of doing.
Sure.
And that's not their fault because it's not their job. Once I ask business people what happens when a competitor drops their price, I start to understand how the business works. I start to understand what's important. I start to understand where the margins are. The requirements start to become clear with a completely different level of understanding than tell me your requirements, which will most of the time just be a description of a system that does something. This makes it much easier for us to be innovative and much easier for us to do this thing that everyone's calling digital transformation, because we're in there with the business trying to understand what it is that we're actually trying to achieve. And so with the combination of the stressor analysis and the flow-based decomposition, we get to a design that has a level of modularity and a level of weak linkage that will allow it will hopefully provably be more resilient than if we had simply sat down and tried to design something that's resilient and use best practices and patterns and frameworks and join the dots methodologies. So what we're actually doing, all these tools are doing, is that they are taking people outside of their comfort zone, outside of this need to have a plan and execute it on, and it's forcing them to partake in real critical thinking, and also to accept the reality that in this complex system, you cannot predict or control, and you have to have other ways of dealing with that inability to predict and control.
So you mentioned a specific flow before: order red bicycle with a bell.
Yeah.
How might that actually be decomposed into modules that maybe people can sort of start learning how to think more concretely? So you've got the stressors that you expect. Well, I shouldn't say that you expect, but the stressors that are likely to occur. And of course, you can't get them all, but you get enough. And then you get the flows that you are going to have through the system. So then what is a modular decomposition that I might expect to see to help accommodate the flows that are going to be going through my system?
So the order bicycle is an example of that's just a single flow through the system. Another flow through the system will be to add a new bicycle to your catalog. Another flow will be to set a sale price on a particular bicycle. So what we'll say initially, we'll have all of those flows, and there'll be quite a number of them, and we ask the question: how should these flows live together, or should they exist as separate flows in order to prevent contagion? And let's take two flows as an example: order bicycle and payment. Or let's say order bicycle and shipping. That's a little bit better. So we have one flow that is order bicycle, and information flows from me, the consumer, to the company, and that has to execute a whole bunch of different functions before it can pass that on to distribution so that they can do their shipping. And so we have the second flow, which is shipping. And so the order comes in, and we check that the bicycle's in our inventory, and we have to do that. We have to check that payment has gone through, and we have to check that I'm a customer. We have to check that you have my address, that information was either in the system already or came as part of the message, that was as part of the flow that was passed. And then we go into the next flow, which is shipping, and then we send a piece of paper to an order to the warehouse that says, put this red bicycle with two wheels and a bell in a box and put this address on it and send it out. And so if we were to do all of that as one single flow, imagine we'd been thinking in terms of use case, and the use case was buy bicycle. Now we expose it to stress, and here's the stress. We've decided that apart from just selling bicycles, we're now also going to sell tractors, which is going to have a completely different method of distribution than bicycles, because it's not something that's going to be, you can't send a tractor through the post the same way you can a bicycle. You're going to need different partners, and so what you have is a completely different reaction to this stressor for across these two flows. And so what we're going to say is we need to separate the shipping flow from the ordering flow. And because they're going to have a different response to stress. When we change the stress, when we bring in the stressor of now ordering tractors, it will hit the ordering, and it will hit the shipping in different ways, and so they don't belong inside the same component. And we do this. It's hard to explain over a microphone, but we do this using design structure matrices that allow us to see dependencies between these different flows. And when we see dependency, that asks us to look for a particular stressor. And so I'm jumping ahead by thinking of what happens if we change the product that we're sending. The second type of matrix that we use is a stressor flow. How does stress impact these different flows? And so if I have bicycles and I have tractors and I add something else and I add cars, then every time I add a new product, it changes shipping, which has an impact on every other product that I'm selling. And so I have to constantly update that shipping module, and that tells me that I need to move shipping out into a number of separate flows. Does that make sense? It's not particularly easy to explain.
I think so. It does to me, to my mind, it harkens a bit back to Parnas, who you mentioned before, and decomposing in order to, his concept, of course, was hiding algorithmic complexity, hiding various things such as, how a function is ordered or the steps in it, things of this nature. But this almost sounds like stressor-based decomposition as maybe a summary of what you're talking about.
Yes, it is stressor based, and there's a level beyond that which I do in my research where the decomposition is actually done using a mathematical tool called a hypernetwork. But we'll not get into that today because we won't have time.
Okay, yeah, that sounds like maybe another topic for another show.
Yeah, it's it's sort of it's advanced geometry, and not everyone finds that entertaining. The concept is that we use stress to guide our decisions around where we are allowed to take dependencies, which is why we use the design structure matrix and the incidence matrices to see what way do these components react to stress. And so what we'll do is we'll identify hundreds of different flows in our system. And some of those, we can't implement every single one of those flows as its own separate system. So what we do is we look for similar patterns of reaction to stress, and we say these flows are going to be hit by the same stressors all the time. There must be some kind of relationship here. Let's bring them into a single flow, and then we do this exactly the same thing to decide which components should be in there, and we do exactly the same thing to decide which functions should be in the components. And it does come back to Parnas a little bit, and it sounds like we're doing encapsulation in order to minimize the surface area. But what we're really trying to do is to increase the resilience of the system, which is how we measure success. So encapsulation, remember, is not the goal here. Even if encapsulation is a byproduct of what we're doing, what we're trying to do is to increase the ability of the system to respond to unknown stress.
So are there some particular techniques that people can use to help them discover what the stressors might be to their system? I guess I appreciate the silliness of getting people out of their maybe rigid mindset by using dragons and things of that nature. But when it comes down to it, for example, I can imagine business people hearing this conversation and saying, this sounds like a lot of upfront design. It sounds like it's expensive. It's going to take a long time. And we just want to start writing software and shipping features. So how do you respond to that? And then are there some techniques that can help you shorten the time frames to identifying your flows and your stressors in your system?
Yeah, so I think if you go and speak to senior architects who are successfully designing and delivering systems, they're doing this kind of thing. It's just very, very difficult for them to articulate. So it doesn't really take that much time. A stressor analysis does not take a great deal of time. But one of the things that we always talk about is this going to increase the cost? And absolutely, if you come up with a solution, a mitigation to every single stressor that you see, it's going to seem like you're building the system to cope with things that are never going to happen. And people will ask, well, is there a justified return on that kind of thing? And here we go back to Tulip, who talks about convex strategies for building systems that are anti-fragile. And what happens is that we look at everything we can do at the design stage that costs very, very little money in order to make it capable of coping with that stress. And that might mean just moving a few functions from one component to another in order to prevent contagion across different flows and to lower the cost of actually making a change if we need to make that change in the future. A lot of that stuff doesn't cost any money. For those mitigations that do cost money, there's the third step after your stressors, after your flow-based analysis. The third step in the anti-fragile systems design process is the trade-off step. And when you have solutions that are concave and that you're going to have to spend a lot of money on something that has a very small risk, then you don't automatically build that into your system. You lift that up to a wider group of stakeholders in the project and say, should we do this or should we not? And in the anti-fragile systems design, we use something, in the simplest case, something called ATAM, the Architecture Trade-off and Analysis Method, as a way of guiding that conversation. And then we're getting into the real world of risk management that our project managers are used to. Now we actually want to talk about, should we manage this risk or not? Should we invest in mitigating this risk or not? Whereas previously what we've been doing is using the concept of stress to push our design in a particular direction.
I see. So if you push your design to the limits to accommodate all stressors, you can come up with this astronomically expensive system that's meant to accommodate every possible stressor. But now you bring that to the actual business stakeholders and you begin to discuss sort of bringing this down to reality. You know, we've considered a system that's expansive and can cover all of these possible bases, but that's obviously prohibitively expensive. And also, not every stressor has the same risk level. So now we're going to kind of bring that down to reality. Am I hearing you right?
Yeah, so all the mitigations for stressors that you've seen that are actually going to cost a substantial sum of money, you bring those. All the ones that don't cost any money or can be mitigated by simple design changes, you implement those regardless of the probability.
Right.
Because we're not interested in mitigating individual stressors. We want to lift the ability of the system to cope with stress. And the result of that work, even if the business shoots down every single one of your concave strategies, which cost a lot of money to mitigate small risks, the system should still be definitively more resilient than it was when we started the design process. Which brings us then to the final step in the anti-fragile systems design process, which is the failure mode effects analysis. And in that, then now we've broken down our system into a number of flows. We've decided which components are going to exist in those flows and which functions should be in there. We then take it flow by flow and we go to our spreadsheet where we have our stressor analysis. We open a second tab and we work through that tab and we write down the failure modes of every component inside each of these flows. And now we're looking at the internal stress in a system, not the external stress. So we're saying, here we have a queue. What are the failure modes of that queue? And we can say that this queue can slow down, it can crash, the server that it's on can crash, it can receive poison messages. And what we'll start to see as we move through that list is that we'll mitigate each one of these failure modes and we'll try to make the system as self-healing as possible so that we detect and fix errors as automatically if possible, but as fast as we possibly can, with as little expense as we possibly can. And as we move down through both of these lists, the stressor analysis and the failure mode analysis, what you'll start to realize is as you move down through these lists, it becomes incredibly difficult to stress the system. It becomes incredibly difficult to find examples of internal or external stress that actually damage your system. And that's how you know you're on the right path, because you've built something that's responding to stress that you have, stress both internal and external, that you haven't seen before. And this leads to something called exaptation. And exaptation is where two functions of a system, two mitigations that we put in place, unrelated, can actually combine to cope with problems that they'd never seen, that the system had never seen before. The example often given is one of dinosaurs. And so back in time, there were these little tiny dinosaurs who had a huge stressor, and that was bigger dinosaurs kept eating them. And so the dinosaurs who had evolved small claws, they survived better because they were able to climb trees and get away from the big dinosaurs that were eating them. But they developed a new problem, then a new form of stress they were exposed to, which was the cold when they were up in the trees, and so the cold was causing them to die. And the ones that had developed feathers, they survived the cold because they had feathers. And then a third form of stress came along, and that was the wind. And sometimes the wind would blow and knock them out of the trees. And one day, one of the little guys with feathers blew out of the tree, stuck out his arms, and got some uplift. And that's how we got birds, not by design, but through mitigating different forms of stress and developing different functions to cope with different types of stress. And they eventually were able to combine those things in a way that allows us to cope with stress that we hadn't thought of or hadn't designed. And so what we're attempting to do here is to replace this uneasiness in architects and say it's okay not to have a plan. It's okay not to be in control. It's okay not to know everything. And it's okay that the reason that you succeeded was based on intuition, and not on following a plan or a process. And this idea of exaptive system design is what we're trying to get to with anti-fragile systems design. It's not something you can ever guarantee, but in all the projects that I have to go into and rescue and do reviews on, if you were to take the four things I've mentioned, the stressor analysis, the flow-based decomposition, the architecture trade-off, and the failure mode effects analysis, if you take one of those techniques and apply it to any project, you'll get a massive lift in quality. If you take all four together, you'll get an enormous lift in quality around the behavior of the system, and also the capacity to actually meet problems that the capacity to meet problems that you've never seen before. There are no guarantees in this, but when you're working with complex systems, then there are no guarantees. Full stop. There's no way to do this and be right all the time.
Well, if people want to get started with learning more about anti-fragile architecture or learning about how they can apply some of these techniques in their own environments, where should they get started?
Well, there is there are some articles published. I've been publishing a series of articles through Cutter Business Technology Journal over the last year. I guess if you go and add me on LinkedIn, you'll see that list of articles there under my publications. There are also courses that we hold regularly. There's a 2-day course on anti-fragile business architecture, a 4-day course on anti-fragile solutions architecture. There's also an introductory course that introduces all of the stuff you need to know in order to be able to do stressor analysis properly, such as what is a business, what's a business model, what is organizational culture, how do I understand all of these things that an architect needs to understand in order to be able to succeed.
And how much of that is also relevant for business people to be learning and becoming more aware of?
It's absolutely relevant, especially if you look at the impact. So one of the things I find is that if you're actually practicing this in the real world as an architect, you start to impact the business model and the operating model, because when you ask about particular types of stress, it might be that business people haven't thought about these things, and they'll need to make changes in the operating model or small changes in the business model in order to be able to mitigate certain kinds of stress. And so what I found is that from my public seminars, I've had a demand from business people, business analysts, business architects who've wanted to learn this, but not go in deep into the flow-based decomposition. And so that's why we've had to create the shorter course.
Okay. So how can people find out more about what you're up to? I think you mentioned LinkedIn before. Are there any other places that they can get more information about you and your company?
I think LinkedIn is probably the best place at the minute. It's where I'm most active. My literature review for my PhD, I'm doing that out loud, so I'm constantly posting what I'm reading and where this stuff is coming from. And so the LinkedIn page is definitely the best place to see what I'm doing, or what's on my mind on a particular day. For courses in Sweden, I work with the Swedish Computer Society, and so checking their website, which is dataföreningskompetens.se for anyone listening in Sweden. Um,
And we'll post a link to that in the show notes too for us English speakers who don't know what you just said.
Yeah. And there you'll see the schedule for the courses. But the LinkedIn feed is where I'm most active. I have a Twitter account as well, which is @TechnologyTulip. It's there's not as much happening there as there is on LinkedIn.
Okay, great. And then you also have your company website, blacktulip.se, correct?
Yes, I do.
Okay, great. Barry, thank you very much for this discussion about anti-fragile architecture.
Yep. Thanks, Jeff. Thanks for having me on.
This is Jeff Doolittle for Software Engineering Radio. Thanks for listening.
Thanks for listening to SE Radio, an educational program brought to you by IEEE Software Magazine. For more about the podcast, including other episodes, visit our website at se-radio.net. To provide feedback, you can comment on each episode on the website or reach us on LinkedIn, Facebook, Twitter, or through our Slack channel at seradio.slack.com. You can also email us at team@se-radio.net. This and all other episodes of SE Radio is licensed under Creative Commons License 2.5. Thanks for listening.